Hello everyone, my name is Xinlong Zhang and I'm an assistant professor at the Department of Chemistry at the Chinese University of Hong Kong. In this video, I'm going to share about our recently developed chemistry automation toolkit called CHEMSMART, which stands for Chemistry Simulation and Modeling Automation Toolkit for High-Efficiency Quantum Chemistry. Before I begin, I would like to share about our research capabilities. We are a computational group in Hong Kong, and we apply computational tools to understand chemical phenomena such as catalysis. One of the main tools that we use is density functional theory, or DFT, which allows us to study detailed mechanisms of catalytic cycles and allows us to predict and rationalize chemical reactivity and selectivity. We also have tools to understand the electronic structures of molecules, such as looking at the frontier molecular orbitals and natural population analysis. We can also do energy decomposition to understand the competing factors between sterics and electronics for affecting chemical reactivity and energy barriers. We also apply computational tools to understand spectroscopy, such as using time-dependent DFT or TDDFT to understand UVVs and also using DFT to understand NMR spectrum. More recently, we are using machine learning interatomic potentials, leveraging machine learning to accelerate ab initio molecular dynamics for catalysis. This helps to improve the picture of steady DFT, and it has the ability to model explicit solvation at reduced costs. Here are some of our current projects. We are involved in code development for automation. For example, we apply Python programming to automate input, file creation, job submission, results analysis, and so on. We are also using Python programming to make easier use of machine learning protocols. We also have applications in organometallic catalysis, trying to understand transition metal catalyzed CH functionalization and CC coupling reactions. Moreover, we also have applications in asymmetric catalysis. For example, looking at organocarbene and organometallic catalyzed reactions. We have looked at chirality at carbon, sulfur, and boron centers. More recently, we are collaborating with Professor Rui Zhu at the National University of Singapore to understand how chiral DNA can catalyze asymmetric synthesis in water solvent. In here, we will introduce the automation tools for computational chemistry that we have developed. So we know that in computational chemistry, the input file preparation and job submission can be tedious, time-consuming, and error-prone. For example, users might use the wrong DFT functional basis or solvent for different structures in the same project. And sometimes users might forget to change the submission script after copying from one job to another or from one server to another. Here are two quotes on the importance of tools. One is that Abraham Lincoln said that, "Give me 6 hours to chop down a tree, and I will spend the first 4 sharpening the axe." And in Chinese, there's a similar saying, 工欲善其事，必先利其器. This means that if we want to do something well, first of all, we have to sharpen the tools that allows us to do those things. So it will be good to have an automated platform that can streamline the input file preparation, create a submission script, and automatically submit the job and execute it. And it should also be able to automatically analyze the results. There will be some desirable features. For example, it has to be easy to use and well documented. And for our CHEMSMART, we have the very detailed reader docs. And in this video and following tutorial videos, we will show how to install and how to use CHEMSMART. It has to be cross-platform compatible, meaning that this tool has to be able to be used on different operating systems such as Windows, Mac OS, or Linux. It has to be highly reusable. It should not be like a collection of bunch of scripts that only allows it to do specific jobs, and each time when you do different job, you have to modify the script on the run. So this tool should be easily reusable for different cases of chemical simulations. The codes should be designed as plug and play and modular, which allows for easy extension. So for example, if we want to have new features or we want to incorporate new software into the tool, it should be easy to write another module to the Python software and incorporate that. It should not allow us to rewrite the whole design structure and revise the whole codes. Here we introduce CHEMSMART, Chemistry Simulation and Modeling Automation Toolkit. So the aim is to simplify and standardize computational chemistry input file creation, job submission, and results analysis. Here are some of the features of CHEMSMART. It has integrated quantum chemistry workflow from input preparation to job execution, results visualization and analysis, and data organization. It is modular in design and it has flexible interface that allows easy extension to incorporate additional software. It is server agnostic commands, so it means that it doesn't matter which server we are running on. We are running on Slurm or Toolk queuing system. The same submission command will be used for submitting a job. So here is the central design idea centered on the central molecule object. So this molecule object is a Python class that incorporates all the information about the molecule. For example, the structure, the energy, the coordinates, and so on. So in CHEMSMART, we have a CHEMSMART.io input-output module that allows us to convert different file formats into a molecule object. So you can convert .xyz, .sdf, .com, .log, and so on and so on. It can also interface with established heterogeneous catalysis methods such as ASE atoms and PyMatrix molecule. It can also interface with chem-informatic molecules such as RDKit. Moreover, we can also be able to read in the PubChem ID, and from the PubChem ID, we are able to create a molecule object, or we can read in small string and create a molecule object. More recently, we also support the reading in of the molecule object from ChemDraw structure in a ChemDraw file. So with this molecule object, we are able to use it to write an input file for Gaussian and Orca, and also input file for NCI plot to analyze the non-covalent interactions. The idea is that regardless of the file format, it can be read into a molecule object and can be read into different software input files. So for example, any file type containing a molecular structure can be passed into the molecule object, and including PubChem ID, small string as mentioned. So files from different software can be interconverted easily, which allows for cross-compatibility between different packages. So due to this design, one may supply Orca file to CHEMSMART to create a Gaussian input file and vice versa. For example, this is useful because, for example, if we run the DFT optimization in Gaussian and get the .log output file, but we want to run the single point calculation in Orca using DLPNO CCST parenthesis T method, then we can simply supply the log file to CHEMSMART and it will write the input file for Orca single point calculation. So how is it different from job submission using software versus submission in CHEMSMART? So first of all, CHEMSMART allows us to automatically generate the input file. So these general settings, such as DST functional basis sets, are saved in projects. And this increased the robustness and improved reproducibility. So later on in our tutorials, we will show how to configure these project settings so that it will be able to run different projects at the same time. It is highly user customizable so that different levels of theory can be used for different projects the user might be running. For example, you may be running organic systems and organometallic systems, which require different functionals, and this can be customized as well by the users without affecting the codes. The server configurations will be taken care of. We don't need to worry about the submission scripts such as number of nodes, memory, wall time, etc. And this will be customizable and configured in the server's configuration file, which we will show later on. So here are the typical folder structure. First, in the home directory, we are able to put CHEMSMART in the bin by git clone the CHEMSMART and installed it. And once we configure, it will automatically set up the home.chemsmart folder, which contains these things. In the Gaussian folder and the Orca folder, we can have these different project settings containing different functional and basis sets to be used for that particular project. So for example, here we have the functional basis set for carbene and different ones for iron and different ones for sulfur projects. And in Orca, we can have the same. And in the server setting, we have the configurations that take care of the server, the computing cluster, including the number of wall time, the memory, the number of nodes, and so on and so forth. And here we also have user settings, which allows you to put in an email that allows to writing of submission script that will notify the user once the job is finished. And then we will set up a scratch directory or a symbolic link to the scratch on the home directory for running jobs in the scratch. So here are the design principles. Again, we have a central molecule object containing everything that the molecule has. And then we have ChemSmart.io that takes care of the input, output, and interconversion of the formats. And then we have ChemSmart.cli, which handles job management, such as job creation, submission, and execution. So this command line interface allows us to submit jobs from the command line using a single command for each job. So we have the ChemSmart.jobs class that takes care of different jobs such as Gaussian Orca job, visualization job, NCR plot job, thermochemistry job, and so on. So each of these calculations is handled as a job. And in future, if we want to incorporate new things, we can easily add new software jobs as a subclass of these jobs without changing the underlying codes. And for each job, it has the job.sub and job.run method, which allows us to submit to the cluster using job.sub or to run it on the local machine using job.run. And we have ChemSmart.settings that take care of the user configurations, server configurations, executables such as looking at where the Gaussian or Orca executable is installed, and it will be configured automatically. And we have these submission preferences. Once the computational job is done, we can have the results using the ChemSmart.analysis module, which then will get all these computational results and attach to the molecule. For example, after a quantum chemical calculation, we have the energy, atomic charges, molecular orbitals, and so on, which can be attached back to the molecule object. And then we have ChemSmart.util, which has the utility functions to help with different requirements. Here are some of the example project and server settings. We will go through this in detail in the following tutorials. So here is the project setting. So for example, here gas will have this, we can specify ab initio like wave function methods of just using DFT with functional basis, or we can specify with semi-empirical methods. So there are a lot of ways to customize this. So for example, if we want to run gas optimization, we can just delete these two lines so that it doesn't run in solvent. But if we want to run optimization in the solvent phase, we can add this. And then this solvent is for single point calculations, a larger basis set, and so on. And if we want to run everything in the solvent phase, we can simply set gas as null. And we will go through this in detail in the following video tutorials. We can also automate TD-DFT calculations by using this TD method for running TD-DFT calculations. And here are the example of server settings. Here is saying that the scheduler is PBS, and there are extra commands which will be automatically added when we configure CHEMSMART. And then here we have the Gaussian executable location, and then some environment and additional modules if needed, depending on the specific cluster that someone is using. As mentioned, there are many other customizations, such as if you want to include DS tag or other things, and there are many different customizations. For example, if we want to use custom solvents, that's also easily specifiable, and we will go through more in detail. So here are the basic submission commands. So first we have CHEMSMART run or sub, and then we have these different sub commands. So there are two execution modes. For example, if we want to run local execution, we can use CHEMSMART run, which will execute the job on the local terminal. This is useful when we want the quick result or when the job is lightweight that can be executed easily. And then we have HPC submission using CHEMSMART sub, which will submit the job for high performance computing clusters. So for example, one can say CHEMSMART sub, Gaussian, Orca, or NCI plot, or thermal chemistry, and so on and so forth. And then you have a dash project, looking at the project setting that we configured, including the DFT functional and basis set and so on. And then we will supply a file that contains the molecular geometry. So as mentioned, this file can be any format as long as it can be passed into the molecule object. We can even give it a PubChem ID or a small string so that it can create a job for submission. And we can do like optimization, TS, more redundant, potential energy scan, and so on and so forth. And we will cover these in the subsequent tutorials. So how does it look like to submit a job using CHEMSMART? So for example, here is a submission command. We just say CHEMSMART sub Gaussian, and then this is the Gaussian software we want to submit. And then -p project setting IN, which contains the DFT functional and basis set for the project. And then we have -f input.xyz, which gives the structure that we want to run on. And because .xyz doesn't contain the charge and multiplicity, we have -c 0 for the charge and -m1 for the multiplicity. And then we say op. So for example, we can also use -c0 -m3 to run a neutral triplet, or -c0 -m5 to run a neutral quintet. And this op is the optimization. So moreover, we can also run using the PubChem ID, as we have mentioned before. Let's say this PubChem ID, and then we have give it a label to give the file name. And because the PubChem structure doesn't have charge and multiplicity, we use -c0 and -m1 for 0 charge and multiplicity of 1. And then we say op for running optimization. So here we will see what it looks like in the video. So we look at that the folder is empty, and then we go to PubChem ID. We can see that there's a PubChem ID containing the structure. We say CHEMSMART run Gaussian, and then project setting, and give a PubChem ID, and then give it a label. So this PubChem ID is the molecule exerting. Give it a label, and then give it a charge and multiplicity, and then say optimization job. So here is just a local run, and then this is the result in the empty folder. Now it creates the Gaussian input file as editing.com. And if we visualize this molecule here, this is the structure that it builds just by using the PubChem ID. And we can check that this is indeed the same structure as what we have on the PubChem. So next, if we want to run other jobs, this is also possible. So for example, CHEMSMART sub Gaussian with IAM project setting a file name, and we say mod rate to do a more redundant optimization in Gaussian. So here we did not specify charge or multiplicity because the input file contains this information. So if charge and multiplicity is not specified, it will use the default in here. And even if let's say the structure is 0 and 1 charge multiplicity, we can override it by -c and then -m in the command line. So for example, you can run the structure neutral singlet structure, and then you can use the optimized structure log file as the input and create a, let's say, single electron reduced species just by using -c charge of -1 -m2 multiplicity of doublet. So here the mod rate have additional command -c using coordinate 1, 2, and 3, 4, 5, meaning the bond distance between 1, 2 is frozen and the angle 3, 4, 5 is frozen. And this will prepare the input file accordingly and submit it. Now, if we have a structure mod rate.log file and we want to use this to run the TS search, we can do so with this simple command. Just supply a file here and say this is the TS job that we want to run. So what happens is that the CHEMSMART will take the last structure from mod rate.log and prepare the input file for running the TS search accordingly. And this is what we can see here. So we have a mod rate.log file that we can visualize. So it has one imaginary frequency corresponding to this deprotonation and CO bond formation. And if we check the root string here for this file, it's a more redundant job. So I'm just going to go to the computing cluster and then go to the folder containing this mod rate file. So this contains the mod rate.log file. Conda activate CHEMSMART to go into the CHEMSMART environment, which we will show how to install later. And then we say CHEMSMART sub xlet. Xlet is the server settings containing all the number of nodes, wall times, memory, and so on. And then we are submitting a Gaussian job with project settings in base. And then we are using this mod rate.log file as the input and run the TS job. So what happens is that this job is created and automatically submitted. As you can see, Q sub here, this is submitted. So this is the submission script that's automatically returned. And you also have the Python run script that's automatically returned. So if we check the queue and we see that this job is indeed submitted and it is running as the last job here. Right? And we can also do other jobs such as potential energy surface scan using the scan here. And for scan, we specify the coordinate 1, 2. We want to scan between bond distance 1 and 2. And with a step size of 0.1 angstrom in decreasing step size, minus here is decreasing, and -n is 20 steps. So let's say we have a scan.log file, which is visualized here, and we want to take the number 18th structure for TS search. What we can do is run this command directly and use -i for index. So we say we want to use index 18, and this will take the scan.log and take the structure 18 and prepare the input file for TS optimization, as shown here in this single command. There are ways to obtain help in CHEMSMART. We can simply call CHEMSMART --help, which will give us a range of different options for CHEMSMART. And we can run CHEMSMART sub help, for example, here. It will give you the options available. For example, we can run CHEMSMART sub Gaussian, sub more for PyMore visualization, sub NCI plot, sub ORCA, or sub thermal chemistry. So all these we will show later accordingly in other video tutorials. So also we can do CHEMSMART sub Gaussian -help, which gives all the jobs that can be run with Gaussian software. For example, we can run the supply com file directly just using the com command, and we can run the tddft using the td command. So here are some of the examples of other jobs. For example, we want to run TDDFT job. We can do so. Let's say this is a Gaussian log file, .log, and we simply say CHEMSMART run Gaussian, the project setting, and then the file, and then TD. So what happens is that it will just create a file for the TD. Here, this is TDDFT. And of course, there are available options to the tddft job command, and we can just do td-help to look at all these available commands. The next job is a thermochemistry calculation that we can do. For example, we have a Gaussian log file already in this folder here. And then we can say CHEMSMART run thermochemistry and file, the log file and the temperature. And this will go through the output file and pass the results for the thermochemistry. Note that this thermochemistry run is different. It's independent from what people may have known from Professor Robert Patton's work on good vibes. So here, those things that can be calculated from the geometry will be calculated from it. For example, the rotational constants and so on. Sometimes in Gaussian, the output file may print stars for these values that exceed the precision level, so making reading the file difficult. And what we can do is to calculate these values based on the optimized geometry, just the coordinates. In addition, we can also choose the atoms by the mass weighted by the natural abundance instead of using single isotopic mass. We think that using the natural abundance average mass is more accurate way because it reflects the real chemical species, which also contains some isotopic forms. We can also do crest conformal optimization. For example, here we have crest conformers.xyz, which is a list of conformers from crest sampling. We can first of all CHEMSMART run more and then give the file and say visualize. This allows us to create a PyMol file on the .xyz file and allowing for us to visualize. So as we can see, this creates the crest conformers.pse, which allows us to open and visualize. And we can see that there are 10 conformers in this crest conformer.xyz. And now I can run Gaussian with the project setting and the file here. And because XYZ has no charge and multiplicity, we put charge and multiplicity. And we say we want to run a crest job with a job title optimization. And the number of conformers that I want to use is 8. So what happens is it will take the 8 lowest energy conformer and create the input file and submit the job automatically for us. So we can visualize this. So each of these structure is taken automatically sorted by the energy, where C1 is the lowest energy and C8 is highest. And because we use dash n equal to 8, we only choose 8 out of whole list of conformers in the crest conformers.xyz. We can also apply grouping strategies. Go back to this example and I remove all these additional files, and we have crest conformers.xyz. And then I can run CHEMSMART run Gaussian, the project setting, the file, and then the charge and multiplicity as before, and then crest job type op. You can use mod rate or TS or whatever, which we will show later. So here -G is IMSD, meaning that it will apply a grouping strategy based on the root mean square deviation of the alignments of these structures and try to figure out the distinct clusters based on the IMSD grouping. So by doing this, we successfully identify 6 distinct conformers for optimization, and all this is automated. And we can do DIAS, distortion, interaction, activation strain analysis. Let's say we have IRC file that connects the TS to the reactant side, as we can see here. So this is the oxidative addition of the aryl iodide into the palladium center. So in distortion interaction analysis, we are able to decompose this into two fragments. One is the aryl iodide, and the other is the palladium ligand complex. So what we need to do in the automated DIAS analysis is to identify all the indexes, like the letters, the atom numbers corresponding to one fragment. And this will be needed to run the job. And the atoms belonging to the other fragment will be figured out automatically. So again, CHEMSMART run Gaussian, the project setting and the file for the input. And we say DIAS, and -- help will give us all the available help options. So here we can see that in DIAS run, we need -I, the fragment indices, to tell which atoms belong to one of the fragment, and the other fragment will be automatically determined. -N gives the every nth point along the IRC point. So let's say in here, for example, I have -I 95 to 112, and then -N 10. That means in this ircf-flat.log file, we will take the geometry at the every 10th point and run this DIAS analysis. So what it does is that it will go to these points and take the structure and run the DFT calculation. And then for each of these points, it will be decomposed as fragment 1, and fragment 2 automatically. So this is based on the indices that's supplied to tell which indices belong to which fragment. So we can see that this job is automatically submitted and automatically run. So if we open the point 1 and point 1 fragment 1 and fragment 2, we can see that this is automatically decomposed correctly, with fragment 1 being the aryl iodide and fragment 2 being the palladium ligand catalyst complex, and the point being the whole complex. And this will allow us to use the CHEMSMART.analysis module to analyze the DIAS results later. NCI plot is also possible to just submit it directly. So in the CHEMSMART environment here, on the bottom left, we can run the job, just call it CHEMSMART sub. On the cluster, I use submission sub, and then the server -s exec, and I'm submitting NCI plot with a log file. So this job is submitted, as we can see here. And then we can see that these are the newly generated promolecular density and gradient cube files. So if this is a log file or any file format, it will be using the promolecular NCI plot. And we can also specify by just a PubChem ID or small string, and then it will create the input file and run the NCI plot for us. But here we can also use the WFN wave function file to run the NCI plot. This will run the NCI plot and use the wave function density as the input to generate the NCI cube files. So we can see that here we have these NCI dense and grad cube files, and then we have promolecular ones as well. So depending on whether the file is a log file or a wave function file. We are also able to run structure for studying reaction from a ChemDraw from input. For example, this is a ChemDraw file containing reactant of 3 reactant molecules coming to form one product. We can just run ChemSmart run Gaussian file, and then here you note that the file supply is the CDXML file and then the charge and multiplicity, because this doesn't contain those informations. And then -I, this is the index slicing to say that I want to calculate all the molecules in the CDXML file. And then I say optimization. So here are the 4 files that we have from this calculation. So if we compare these molecules with the ChemDraw structure, we can see that this molecule is the imidazole here. And then this is the diazole compound here. Note that even though this is CBZ abbreviation, the ChemSmart can figure out and build the molecule correctly. And this is the conjugated ketone here. So we can see the product here. We see this is the imidazole group, and then the carbonyl group, and then the nitrogen, which is underneath. So take note of the chirality. This chirality is correct. And then you have this imidazole group here. This is on top. The chirality is all correct. So this allows us to easily do high throughput screening because we can all put the molecules in one ChemDraw file and run it in one submissions command. We can also visualize molecular orbitals. So for example, here you have a checkpoint file, and then we can say ChemSmart run more, and then with the log file here, and then we say mo -- homo. So here it will call the Gaussian executable form check and convert the checkpoint into formatted checkpoint file here. And then it will build the homo cube file and generate the PSE file automatically. It can also build the LUMO automatically, as we can see here. And of course, again, we are able to call for help by using -- help. And these are all the available options. For example, homo LUMO, and we can use -n or number to just plot any molecular orbital we want. For example, here -n31 will plot molecular orbital 31 here automatically, as we can see here. So that was in the cluster where the Gaussian executable is needed. And then here I'm just going to copy those over into my local machine. And if I open this with PyMore, we can see that this is the HOMO of the molecule that's automatically generated. And we can look at the LUMO as well. That's also automatically generated. And we can look at molecular orbital 31 as well. Okay. So we are also able to plot non-covalent interactions. So for example, we have the dense and the cube file. We just say ChemSmart run more, and then NCI, and then this will generate a PSE file automatically. And then we can just open with PyMore to look at this. Okay. We can use -- help to see that these are additional options. For example, binary will plot the NCI plot in 2 colors only. We can just do it -b for binary. And we can see that we have this binary.pse. So 2-color plotting. So we have also done QMMM automation in Orca and Gaussian, and we will have similar video tutorials subsequently. So CHEMSMART is fully open source, and here is our GitHub code, and read the docs and preprint. Please feel free to follow the videos and follow the read the docs instructions and explore to see how it may help in speeding up the efficiency of your computational chemistry workflows. And if you have any issues or any feature requests, please feel free to go to the CHEMSMART GitHub page and leave comments for us. Thank you. And this is my group member who have done these coding works together. And thank you very much. And see you in the next video tutorial.